That hopefully for those that found it still a bit difficult, show the structure of how you generate these constraints. So if you look very closely, so this is a prefix of this guy, this is a prefix of this guy, this is a prefix of this guy. These are basically it's prefix of each other. So C that this first sequence A maps to C plus y minus ya greater than equal 0. Second one maps to C plus xa minus ya minus yd greater than equal 0. And the third one, ABB maps to C plus xa plus xb minus ya minus 2yb. And ABBC maps to C plus xa plus 2xb minus ya minus 2yb minus yc. So I hope that you start seeing that the constraint or inequality in this level is basically the one of the previous level, but on the x side we add this b, and on the y side we add this c. It's constantly what's happening. So you kind of grow. So basically this guy is a, b, b, a, b, c plus xa plus 2xb minus ya minus 3yb minus yc. And if you look at the next level, you see that the only thing that changes is this 2xb becomes 3xb, because this b is here. And the 3yb becomes 4yb because this b is here. That's how these constraints are constantly generated. Use one chalk during the lecture. So, let's take a look here. This is a much more simple event where L is ABBA. So we have four constraints: C minus YA, C minus YB, C plus XA minus YA minus YB. and the last one c plus xb minus y a minus yb, all should be greater than or equal 0. Now, if you don't understand still how these are generated, just assume that these are the constraints that we generate from the event log. Now let's take a look at this place. So as I've been trying to indicate, this place can be characterized in terms of the decision variables as being, it has this c or m value of 1, that is a token, and there's an outgoing R to A, so ya is 1, and all the other variables are 0 because it only has this one arc. Now what we do is we fill out these different values here, and we can all do that, of course. It's very easy. So c is 1, ya is 1, so this would become 1 minus 1, that is 0, and 0 is greater than or equal than 0, so this first constraint is satisfied. Second constraint, c is 1, yb is 0, so 1 minus 0 is 1, greater than or equal 0. Third constraint, c plus xa minus ya minus yb translates to 1 plus 0 minus 1 minus 0. So 1 plus 0 is 1, minus 1 is 0, minus 0, 0. This is satisfied. And the final one, c is 1, xb is 0, ya is 1, yb is 0. So 1 plus 0 minus 1 minus 0 is 0. Okay. And it's also greater than 0. That's how it works. If you generate these constraints, but you do that from that set of sequences or that set of sequences, you can now, for any possible place that we can think of, we can deduce these values based on the place, and we can verify whether that place makes sense or not, given the input event log. So now another example would be this place, for which we now have c again, so this variable for the marker is 1. Now the yb value is 1, and the other guys are 0. And similarly to our previous example, this one will also have all constraints equal to at least 1 and some 0. Sorry, so at least 0 and some are 1. So they are satisfied. In this case, the flower, basically the flower place for these two activities, because everything is 1, you will always have 1 minus 1, 0, 1 minus 1, 0, 1 plus 1 minus 1 minus 1, 0, 1 plus 1 minus 1 minus 0, so it's also fine. This guy, however, is not fine. Why? Because the last two constraints will lead to a value of minus 1. So c is 1, xa is 0, so 1 plus 0 is 1. But ya and yb are both 1, so 1 minus 1 minus 1 is minus 0. And the same holds for the second one. 1 plus 0 minus 1 minus 1 is not greater than or equal to 0. If we add xb, then this last one would become okay, because we would have 1 plus 1 minus 1 minus 1, so 2 minus 2 is 0. But this guy still is false, so c plus xa. So what we can do is, from a high-level point of view, we have an event log, we generate this body of constraints, or a body of equations based on these different variables that we have, and this allows us, for each possible place you can think of, to say, this place allows for the behavior described in the event log, or it doesn't. So this place doesn't, because technically it blocks executing AB. That's also reflected by this constraint. So, now the question is, we know about regions, so any place that is okay, so any place like this, that's what we call regions. So the variable assignment here is a region corresponding to this place. Places, regions are basically the same thing. But the question is, finding work on that. How do we do that? So the constraints of this language-based region theory that we have just considered, they describe a collection of regions, also already asked earlier. So there's a whole bunch of variable assignments, aka places, that all allow for all behavior that we observe in the log. Again, to give you an example, if we have ABD, ACD, we get this body of constraints out of that, and we have this place which would be fine given this body of constraints, and this place is also fine. But given this event log ABD-ACD, we don't really want the top one, but we do really want the lower one. Why? Because in this very simple example, we can see that there's simply a choice between doing B and C. Right? So always do A, always do D, only B or C is executed. So somehow we want to find this place and we don't want to find that place. So how do we do that? When we look at assigning arcs to the places, we observe a few interesting facts. Namely that when we remove output arcs and we add input arcs, we cannot really jeopardize feasibility. So what does it mean is that if we have the place, if we remove this guy and we remove this guy and we add all these guys, we know that whatever this guy allows for, this guy will also allow for. Because the outgoing arcs are going to constrain the behavior, yet the incoming arcs will only basically put more tokens. So that's always fine. Same holds for adding a token. So if we have this place and we add a token, it's fine. However, at the same time, we want to actually find the opposite. So we can combine these two regions, which essentially has a token and an outgoing arc. Now it also has an additional incoming arc. But we don't want to find this type of place. What we actually want is, we want a place that is as expressive as possible, so that is as restrictive as possible. So the example I just gave you, you can always add tokens, you can always add incoming arcs, and we'll never jeopardize. But we want to do exactly the opposite. And furthermore, what we want is, if we have places that look like this, and there exist two alternative places or regions which combine like this, we prefer these two over the other two. So this first concept is known as a minimal region. So essentially, this is not a minimal region because it is the linear combination of these two regions. And we don't want to find non-minimal regions. And that's actually interesting because in state-based, transition-based region theory, we had the same idea. We didn't want to find all regions, we wanted to find minimal regions, those regions where removing a state from the region would jeopardize the thing being a region. Here we also want to find minimal regions, those are regions that are not a linear combination of two other regions. The problem with that is, still there exist regions that, in for example this case, if you just have to log A, B, C, we can find quite easily the region P1 or the place P1 and the P2. Yet P3 is also a region and it's also minimal. Yet we don't want it. So this P3 guy is minimal and we don't. Essentially, it is redundant because there exists a set of places where somehow its marking is always greater or equal than the combined marking of the other elements. So whatever you put in P3 is always the sum of what you put in P1 and P2. It's redundant. Now, what we therefore use is target function and first one. Yeah, so what we're going to work towards is we're going to use these constraints in the context of linear programming. Has anyone never seen linear programming before? Okay, most of you have, great. So these constraints that we have, somehow we have a set of variables and we have linear wave constraints. So that seems to us that using integer linear programming could be very interesting to actually find interesting regions. Now, to quickly summarize how integer linear programming works, if we would have two variables, x and y, not to be confused, by the way, with the variables I've been using so far, so just assume these are two variables, x and y, in a two-dimensional system, and we want to maximize 6 times x plus 5 times y, subject to the following rules. 2x minus 5y should be at most 6, 6x plus 4y should be at most 30, x plus 4y should be at most 16, and both have to be at least 0. What we can do is we can draw basically these different lines. The blue lines here represent the different constraints, and everything within this field here is known as the feasible region or solution space of this linear program. So essentially, any point you can pick in this yellow region, or yellow sort of object, is a solution that satisfies these constraints. At the same time, what we want is we want to maximize this function. So we want to pick some point in this space that maximizes the function. So the optimal LP solution, which is the optimal solution which allows for fractional values, is 2.4x and 3.4y, so that's somewhere here. That would be the optimal solution to this maximization function. But in some cases, we're only interested in integer solutions, so that's non-fractional. So all integer solutions here are depicted by black or red dots. So the black and red dots represent integer solutions that fit this set of constraints. And one of these red guys is maximal. That's actually 4, 1. That is a message. 4, 1 is 1, 2, 3, 4. Okay. I didn't count that, but anyway, you get the point. So this yellow surface is the set of all possible solutions in the real space that adhere to the constraints. The black and red dots represent the black and red dots represent integer value solutions, and actually the optimal solution is just not highlighted here, is 4, 1. So meaning 1, 2, 3, 4. This is the optimal integer solution, and the red solution is the Pareto optimum. I'm not going into detail. So I guess every one of you knows this. Yes.
I'm not sure whether your optimum LP solution is actually correct, because I think those are actually always at some edge.
Yeah, that's also why I was.
And I think it's 2.8 and 3.3. Yeah.
Okay. Well, this is a picture from the interwebs, so could be that the interwebs are wrong. You're right. But,
okay. Sure.
Probably you're right. But you get the point, right?
Yeah.
Because I'm not going into detail on how to compute this, and actually, fun thing, I actually found when I was doing this with alignment calculation, I found a bug in one of the Python libraries that is commonly used. Forgot to report it though. So maybe some rockets will crash into my non-communication skills. Anyways, we use this as a black box. So we just assume that we can either maximize and minimize some function over variables x and y, subject to a body of constraints. Now, I already explained to you in great detail, and I hope it's kind of clear how, in the context of process mining, we can generate a body of constraints that allows for all behavior in event log. There's also an objective function that we can use for that, and that's written like this. Now, for the sake of time, I'm not going into too much detail in the objective function. The only thing you need to know about the objective function is that it favors both minimal regions and regions that have a maximum number of outgoing arcs, so maximize the y component and minimize the x component. So basically this is the ILP formulation in matrix form. I didn't have time to explain the matrix form, but it essentially describes this. And as I said, if you give this to an ILP solver, because we're only interested in finding integer solutions, if you give this to an ILP solver, it will give you the place that has a minimum number of incoming arcs and a maximum number of outgoing arcs. And this is nice. So, actually, I want to skip this for the sake of time. So, one example is that essentially, what if we have ABD, ACD, we have this constraint body that we already seen before, and now we minimize the objective function that you can find in the papers, reading material, also in the slides, because I want to focus for the last 10 minutes on the question how to add solutions. But because I can give this to an ILP solver, and as I said, it will give me integer solutions of assignment to variables, which I can translate to a place which minimize the incoming arcs and maximize the outgoing arcs, but I still get one place. And a Petri net, even for this simple example, ABD, ACD, that we want to find, does not contain one place. So the question is, how do we find multiple places? And essentially, there's two strategies for this. We can try to discover a region and or place for all possible pairs of activities we can make in the event log. And the second approach is we can exploit causalities in the event log. Now, in principle, if I want to connect two places between two transitions with the activity level A and B, so connecting a place that has an incoming arc from A and an outgoing arc to B, I can extend the ILP with these three constraints. So I can say, I construct my basic constraint body, and I say, well, whatever you find, at least put the x value of A to 1, meaning we get a place with an incoming arc from A, and set the y value for B also to 1, meaning we at least have an outgoing arc to B, and furthermore, I don't want to have, so this is again this marking variable, I don't want to have an initial token. So that's how, it's an example of how to find places that connect A and B, going from A to B. If I would like to add an additional token, I can put it to 1, and if I don't specify anything, the solver is free to choose. So basically, this basically shows that whatever we will find with using this ILP, we always have these two arcs in the solution. So again, I can generate all possible pairs of the activities. So in the case of A, B, C, D, this is A, B, A, C, A, D, B, A, B, C, B, D, also B, B, A, A, etc. And if I do that with this simple event log, so I solve an ILP for each possible combination I can make, so AB, AC, AD, AA, BB, BA, BC, etc. This is what I get. So it's a way to no longer find all the possible places. At the same time, we still get a lot of redundant places that we're not really interested in. The second approach is to exploit causality in the event log, and that generates much more suitable results. So essentially what it means, if we have this event log ABD, ACD, and you would, for example, use the causal relation that's defined by the alpha minor, meaning if A is in front of B and B is never in front of A, there's a causal relation, which we have in this law. I can mine a place for each of these arcs here. So I can mine a place for the causal relation between A and B, A and C, C and D, and B and D. So I now know I get at most 4 places, and each of these places somehow reflects causality in the event log. So again, if we do that, so for example, we mine a place for this arc from A to B, we specify that we want the x variable of A to be 1, the y variable of B to be 1, and the marking variable to be 0. And if we do so, we actually get this model, and I cheated a bit because these two causal relations will both result in this place, and these two causal relations will both result in this place. So here, the fact that we get this place is due to this objective function that tries to minimize the incoming arcs and maximize the outgoing arcs. So that's nice. So we already get a Petri net that somehow more accurately starts reflecting this event arc. But we are of course not satisfied with this result. Why? Essentially, this A can be fired at any point in time, as much as we want. It's not really a workflow net because it has no source and sink. We don't know what behavioral properties hold, etc., etc., etc. So basically, no idea, blah, blah, blah. Let me see why I did these slides. I have no freaking clue. Okay. I do. Let's assume I'm also using this log. And I'm doing the same trick, but I'm using ABD, ACD, and also AD. Then if I do this causal trick, what I get is this Petri net. And the problem is that if I replay AD, I have a token remaining in this place. So, with respect to soundness and workflow nets, this is problematic if we apply this basic strategy as I explained to you, because we do not enforce in any way any behavioral properties. A partial fix that we can apply is enforcing that each place is empty after the trace in the log is finished. And we do so by adding constraints that look like this. And I have an example for that. So, if we would like to say every place should be empty after we complete the whole trace, we basically say that C plus XA plus XB plus XD minus YA minus YD is 0. That's based on this trace. This trace generates this constraint, and AD generates this constraint. So basically, it's exactly the same as what we do in building this constraint body, but we use the whole trace for both the X and the Y component. So if we add these constraints, we are sure that any of the traces that are in the log, if we replay them in the Petri net that we find, we have all these places to be empty. So when I did not do that, I got this model where we knew that this place 0 would be having a token if we do A and then D. If we add these constraints, the difference is that now, if we fire ABD, ABD, and ACD and AD, all these 3 places will be empty after you do so, for example. But the problem is that we have, of course, much more behavior. So on the one hand, this is a nice fix. On the other hand, it generates some big problems. Now, one trivial fix that we can apply to kind of limit this infinite behavior to some degree is to add unique starts and ends. Oh, actually, that's not to limit the infinite behavior. But if let me back up for a second. So, the problem is with this model is that on the one hand, everything is empty after we display the stuff, but still I can fire A infinite many times, so I can get infinitely many tokens in these places. Now I don't want that. In this specific event log, I have unique start and end activities. So what I can trivially do is I can add one place to A, being a source place with one token and one sink place here. And I basically know that if I fire A, I can do some stuff here, and then eventually I finish with D. So still this Petri Net is severely underfitting, but I created a workflow net, which is actually sound. And this, in principle, holds for any event log that has unique start and unique end transitions when activities when we apply this minor technique. However, these workflow nets that we find are not sound, but they're relaxed sound. And given that I have only 1 minute left, and I don't want to bother you with that, I am going to skip that. Yeah. So, bottom line. Morale of the story is, I hope that you saw that we can translate event logs into prefix closed languages, we can translate it into body of constraints, which serve as a basis for interlinear programming. Due to sake of time, I was not able to explain to you how the objective function works. There's papers about that which you can definitely read. Some of them I've written. What's most important for the exam, I always tell this in the end of the lecture because otherwise no one comes to my lectures, that you have to be able to construct the constraint body of these IFPs, but you also have to be able to construct the objective function. So I haven't been able to go into detail, but there's examples in the slides, and constructing the objective function is not difficult at all. It's actually, you can basically derive it from the constraint body. So you have to look into that. There will be several examples in the exercises and the exams where you can practice with that. And sadly this year I could not show you why you can find relaxed sound workflow nets, but such as that. So Lisa will now do the instruction session, and as she indicated, she will spend a little time discussing the exercises, and we will be around to answer any specific questions you might have, also related to the lecture. I can imagine something will not clear. So thank you for attending this lecture, and next week there's no lecture, so enjoy the advanced process mining track.